Okay, as is to be expected, not all fluids exhibit Newtonian behavior. And the fluids that don't exhibit Newtonian behavior are called non-Newtonian fluids. This is our Newtonian fluid, a straight line passing through the origin of the tau yx versus the shear rate minus dvx dy graph. You could have a fluid that is something like this. Okay. It starts not from the origin, or it does not pass through the origin, but passes through a certain y-intercept. Okay. So, what do you think this kind of a fluid will behave as? Can you think of that? You see, there is the hint is the shear rate, which is the variation of velocity with distance. When it is 0, there is a certain shear stress, and only beyond that do you have some value for the shear rate itself. Okay. So, that is the hint here. Think about it. Pause the video here, think about it, then come back. We will discuss. Okay. Typically, this intercept is called tau naught, or the yield stress. This kind of fluid exhibits this kind of a behavior is called a Bingham plastic. And what Bingham plastics do is that they don't move. There is no velocity gradient. There is no change of velocity with distance until a certain tau 0 is applied. And beyond the tau 0, it behaves like a Newtonian fluid. Therefore, there is a certain yield stress that is required to make it move. And after you make it move, then it behaves like a Newtonian fluid. Okay. This is the characteristic of a Bingham plastic. The Bingham plastic does not flow until a certain minimum shear stress tau naught is applied. The shear rate is 0 until tau yx is less than 0. Yield stress we talked about. Okay. And an example of such a fluid is the toothpaste that you use every morning. Okay. You take a toothpaste, you just keep it there, nothing is going to move out of the paste tube. You press it, you provide a certain yield stress. Once it crosses a certain yield stress, then it starts moving. Okay. So, that is a very standard example of a Bingham plastic, remember that. Mathematically, the Newtonian fluid was described by the Newton's law of viscosity, tau yx equals mu times minus dvx dy. So, this Bingham plastic is described by these set of equations, tau yx equals tau 0 minus mu times dvx dy. If tau yx is greater than tau 0, if not, if dvx or dvx dy equals 0, if tau yx is less than tau 0. Okay. So, it does not move till this is applied, and after it is applied, it starts moving and it shows a typical Newtonian behavior. Of course, it does not pass through the origin, it passes through tau 0. That is why you have an intercept here, y equals mx plus c kind of a thing. So, we will call the first one 3.1-2a, the second one as 3.1-2b. Okay. So, we saw a Newtonian fluid and a Bingham plastic. Those are not the only ones there. There are many more complex fluids in nature. Blood is a very complex fluid. The viscosities of Newtonian fluid and Bingham plastic are independent of shear rate. They were constants. Okay. They were not dependent on the shear rate. However, the viscosity could be dependent on the shear rate for certain fluids. It can always happen. The fluid will become either easier to flow or more difficult to flow with an increase in shear rate. That is what it means. Okay. Which means, if you stir harder, certain things will become harder to stir and certain things will become easier to stir as you increase the speed of stirring. That is what it means. So, on the rheological characterization graph tau yx versus minus dvx dy, This is the Newtonian fluid and this is the Bingham plastic with tau 0, the yield stress. And these fluids are either like this, which is shear thinning. Okay, the viscosity decreases with increasing shear rate. So, the faster you stir, the higher the variation of velocity with distance, and lower is its proportionality with shear stress, which means it becomes shear thinning. Okay, it becomes easier to stir if you increase the speed of stirring. At higher and higher speeds of stirring, which is given as you move in this direction, it becomes a flatter curve. It could also move in the other direction. As you stir it faster and faster, it becomes more difficult to stir, and that is represented by this curve. The shear thinning is called a pseudoplastic fluid. The shear thickening is called a dilatant fluid. Okay. Pseudoplastic fluids, typical paints are pseudoplastic. You stir faster, it becomes easier. And quicksand is a very good example of a dilatant fluid. The faster you try to move, the more difficult it gets to move, okay, because the viscosity increases with shear rate quite steeply. Pseudoplastic fluids and dilatant fluids are known as power law fluids because of the way we mathematically represent them. Because the variation of a particular apparent viscosity with shear rate can be expressed as a power law. What I mean by that is, the equation that describes this behavior, either this or this, is tau yx equals minus m dvx dy to the power of n minus 1 dvx dy. So, you have this term depending on the shear rate. Okay, that is what I meant by now the viscosity is being dependent on shear rates. The apparent viscosity, which is this term, is given as m times dvx dy to the power of n minus 1. This negative actually goes with this, we all know that. And equation 3.1-4, m and n are the parameters that are dependent on the fluid. If n equals 1, the dependence on shear rate goes away and you get back your Newtonian fluid, m equals mu, the Newtonian viscosity. If n is less than 1, the fluid will be shear thinning or pseudoplastic, which is this. If n is greater than 1, the fluid is shear thickening or dilatant, which is this. Okay. So, these are the mathematical representations which will become useful. What I would like you to do is watch this video. Okay, I cannot show you this video here for obvious reasons. They are available from standard sources. This will give you it's a fun video and it will give you an idea of at least one type of fluids. This is called "These People Are Walking on Water." It's a fun video with a lot of peppy music associated with it and so on and so forth. Please watch this. And why is ketchup so hard to pour is another video. Okay, this will explain how the molecular nature of the substance of ketchup determines why it becomes so difficult to pour. Okay. So, I would recommend that you watch these videos. Apart from this, there are other fluids also. Okay, and some of those are biologically very important. They show time dependent behavior. Okay. The shear stress depends on the shear rate as well as on something called a strain, which could be either elastic or Hookean. Do not worry too much about it. And a common constitutive equation to describe viscoelastic fluids is what is called the Maxwell model, which is given as this: tau yx plus mu by g dou t. This is the time variation that is brought in here, the history brought in here, dou t of tau yx equals mu times minus dvx dy. G is the shear elastic modulus, Newton per meter squared, and the synovial fluid that lubricates joints in the human body is a viscoelastic fluid. Also, I think the hyaluronic acid, yes, the hyaluronic acid is which is present in the eye and so on and so forth, which provides a lot of lubrication, which is the important protein in the synovial fluid also. This itself is a viscoelastic fluid. Mucous and vitreous fluid in the eye exhibit viscoelastic behavior. It has hyaluronic acid present in it. At least the vitreous fluid has that. You could watch these two videos, Introduction to Viscoelasticity as well as Fluid Dynamics Non-Newtonian Fluids, to gain more appreciation of these kinds of fluids, viscoelastic fluids, which will be nice. Blood is a very important biological fluid. Synovial fluid is also important. Blood, we all know, it's a highly complex fluid. Books have been written on blood rheology. It consists of plasma, which is a mixture of liquids, proteins, and many different cells. We all know this: erythrocytes, leukocytes, and so on and so forth. Blood behaves partially as a Bingham plastic. It exhibits a yield stress and behaves partially as a viscoelastic fluid. Okay, time dependent behavior, and so on. The complex rheological behavior of blood also arises from the clumping of RBCs, erythrocytes, due to the fibrinogen on their surface, apart from the complex composition of blood. And as I said, there are books written on blood rheology. It's a field in its own right. And one of the models that is used to describe blood rheology is what I'm just going to present in this introductory course and leave it at that. You need to know what kind of model is used, and that's the reason I'm giving you this. We won't deal too much or delve too much into this model. The Caisson model is something like this: tau per half equals tau naught per half plus mu per half times the absolute value of minus dvx dy to the power of half. This is the Caisson model which describes blood rheology. Tau naught is the yield stress, and rest you know. The yield stress actually depends on the volume fraction of erythrocytes, RBCs, in the blood. Okay, so the yield stress is dependent on that, and the volume fraction of erythrocytes in blood is typically called the hematocrit. These are names that you need to know. Directly impinges on the blood rheology. A typical value for the hematocrit is 0.4. Interestingly, at low shear rates of less than 20 second inverse, the blood shows complex behavior. So, if the blood is flowing slow, then you need to worry about the complex nature of blood. If the blood is flowing fast, as in some blood vessels, then it behaves very close to a Newtonian fluid. Okay, that's what happens. So, if you are studying the blood flow in probably certain large arteries, you can approximate it to Newtonian flow, and there won't be much of a problem at all. That is here at high shear rates greater than 100 second inverse, the blood can be assumed well to behave as a Newtonian fluid. You might want to watch this video to gain better understanding, appreciation, and so on. Whole blood viscosity links to cardiovascular disease. Please watch this recommended video. Okay. So, what we looked at so far is the relationship between shear stress and shear rate, which is a standard characterization for fluids, the rheological characterization, the different types of fluids, Newtonian fluid first, shear stress, shear rate, the straight line passing through the origin. Then we had a Bingham plastic, shear stress versus shear rate, again a linear curve but not passing through the origin. Then a pseudoplastic fluid, a dilatant fluid, and then we went into fluids whose viscosity depends on the shear rate, viscoelastic fluid, and also there could be a time dependent variation. And then we briefly looked at blood, which is a highly complex fluid, rheologically speaking, and even otherwise it's a highly complex fluid, and the Caisson model is used to describe that. When we meet next, we'll take things forward. See you then.